The gas turbine engine stands as a cornerstone of modern power generation and propulsion. At the very core of this intricate machinery lies the combustion chamber, often referred to simply as the combustor. This component performs a critical function. It is here that chemical energy stored within a fuel is converted into thermal energy. The combustor acts as the engine's furnace, generating the high-temperature, high-pressure gas flow that subsequently drives the turbine stages. Without an efficient and reliable combustion chamber, the entire gas turbine system would fail to operate. The primary role of the combustion chamber is to add heat to the compressed air flowing from the compressor section of the gas turbine. This heated gas then expands through the turbine, producing power. The design of a combustor must achieve several demanding objectives simultaneously. It must ensure stable and complete combustion of the fuel over a wide range of operating conditions. Furthermore, the combustor must minimize pressure losses as the air flows through it, as significant losses reduce overall engine efficiency. The performance of the entire gas turbine engine is profoundly influenced by the design and operation of its combustion chamber. An efficient combustor ensures maximum energy release from the fuel. Combustion is fundamentally a rapid chemical reaction between a fuel and an oxidant, typically air, that produces heat and light. In a gas turbine combustor, this process involves the oxidation of hydrocarbon fuels. The primary products of complete combustion are carbon dioxide and water vapor, along with the release of significant thermal energy. The physics of this transformation is governed by principles of chemical kinetics, thermodynamics, and fluid dynamics. Combustion processes can be broadly categorized into laminar and turbulent regimes. Laminar combustion occurs when the fluid flow is smooth and orderly, with fuel and air mixing primarily through molecular diffusion. In contrast, turbulent combustion dominates in gas turbine applications. Turbulence is characterized by chaotic, irregular fluid motion, with eddies and vortices of various sizes. This chaotic motion significantly enhances the mixing rate of fuel and air. The increased mixing accelerates the chemical reactions, leading to a much faster and more intense combustion process. Gas turbine combustors are designed in several distinct configurations, each with its own set of advantages and disadvantages. The three main types are can-type, annular, and can-annular combustors. Early jet engines often utilized can-type combustors. This design consists of multiple individual cylindrical combustion cans arranged circumferentially around the engine's central shaft. Each can operate as a separate combustor, with its own fuel injector and air supply. Can-type combustors offer several benefits. They are relatively simple to design and develop, as a single can be tested and optimized independently. Maintenance is also somewhat easier, as individual cans can be replaced if damaged without requiring disassembly of the entire combustor section. The annular combustor represents a more advanced design, commonly found in modern, high-performance gas turbines. It consists of a single continuous combustion chamber in the shape of a ring or annulus, concentric with the engine axis. Annular combustors offer excellent thermodynamic efficiency and a more uniform outlet temperature profile compared to can-type designs. Ensuring reliable ignition and maintaining a stable flame across a wide range of operating conditions are paramount for gas turbine combustors. This is achieved through careful design of burners, the incorporation of swirlers, and various flame stabilization strategies. The burner assembly, located at the upstream end of the combustor, is responsible for introducing fuel and air in a manner that promotes efficient mixing and combustion. Swirlers are crucial components within the burner assembly. They impart a rotational motion or swirl to the incoming airflow before it mixes with the fuel. This swirling motion creates a complex aerodynamic field characterized by a central toroidal recirculation zone. The recirculation of hot gases provides a continuous source of ignition for the incoming fresh fuel-air mixture, thereby anchoring and stabilizing the flame. Gas turbines are versatile machines capable of operating on a variety of fuels, ranging from natural gas and liquid petroleum fuels like kerosene, also known as jet fuel, and diesel, to lower-grade fuels such as syngas or even hydrogen in future designs. The choice of fuel significantly impacts combustor design, particularly the fuel injection system and combustion characteristics. Gaseous fuels, such as natural gas, are relatively easy to mix with air and typically burn cleanly. Liquid fuels, however, must first be atomized into fine droplets to increase their surface area and promote rapid evaporation and mixing with air before combustion can occur effectively. Fuel injection systems are critical for delivering the fuel to the combustion zone in the correct state and distribution. For liquid fuels, atomizers are employed. Common types include pressure atomizers, air assist atomizers, and air blast atomizers. The quality of atomization, characterized by droplet size distribution, directly affects combustion efficiency, ignition, and emissions. The strategy for fuel injection also depends on the combustion concept being employed. Combustion chambers operate under extremely harsh conditions, with gas temperatures often exceeding 2000 Kelvin, approximately 1727 degrees Celsius, or 3140 degrees Fahrenheit. Therefore, sophisticated material selection, advanced thermal management, and effective cooling techniques are absolutely essential for the structural integrity and operational longevity of the combustor. The materials used for combustor liners, transition pieces, and fuel nozzles must possess high temperature strength, excellent oxidation and corrosion resistance, and good thermal fatigue properties. Nickel-based superalloys, such as Hastelloy X or Haynes 188, are commonly used for combustor liners due to their ability to retain strength at elevated temperatures and resist oxidation. For even higher temperature applications, ceramic matrix composites, or CMCs, are emerging as promising alternatives. The application of thermal barrier coatings, or TBCs, is another critical aspect of material strategy. TBCs are thin ceramic coatings, typically yttria-stabilized zirconia, applied to the hot gas side surfaces of combustor components. These coatings provide thermal insulation, reducing the metal temperature underneath. Cooling techniques are vital to keep the combustor wall temperatures within acceptable limits, ensuring the material's structural integrity. Beyond efficient combustion and flame stability, two other critical performance parameters for a gas turbine combustor are the minimization of pressure loss and the achievement of a uniform temperature profile at the combustor exit. Pressure loss, also known as total pressure drop, refers to the reduction in the total pressure of the airflow as it passes through the combustor. While some pressure drop is inevitable due to friction, heat addition, and momentum changes associated with mixing and combustion, excessive pressure loss directly penalizes the overall thermodynamic efficiency and power output of the gas turbine engine. The sources of pressure loss within a combustor are numerous. They include frictional losses as air flows through intricate passages, diffusers, and swirlers. Momentum losses occur due to the turning of flows and the mixing of different air streams. The combustion process in gas turbines, while essential for power generation, inevitably produces emissions that can have adverse environmental impacts. Key pollutants of concern include oxides of nitrogen, NOx, carbon monoxide, Colorado, unburned hydrocarbons, UHC, and particulate matter, or soot. Increasingly stringent environmental regulations worldwide are driving significant research and development efforts to reduce these emissions. NOx, comprising nitric oxide, NO, and nitrogen dioxide, NO2, is formed primarily at high flame temperatures through the oxidation of atmospheric nitrogen. CO and UHC are products of incomplete combustion, typically occurring at lower temperatures or in fuel-rich zones. Strategies to control NOx emissions often focus on reducing the peak flame temperatures within the combustor. One common approach is lean combustion, where the engine operates with an excess of air relative to fuel. This results in lower flame temperatures, thereby inhibiting NOx formation. Lean premixed pre-vaporized, or LPP, combustion is an advanced concept where liquid fuel is vaporized and thoroughly mixed with air before entering the combustion zone, allowing for very lean, low-temperature combustion. The quest for higher efficiency, lower emissions, and greater fuel flexibility continues to drive innovation in gas turbine combustor technology. Researchers and engineers are exploring a range of advanced concepts and novel materials to meet the challenges of the future. One significant area of development is ultra-low NOx combustion systems. These include advanced lean burn concepts like lean direct injection, LDI, and further refinements of LPP systems, aiming to achieve near-zero NOx emissions without the need for post-combustion catalysts, or by minimizing their size and complexity. The use of alternative and sustainable fuels is another major driver for combustor innovation. Hydrogen, as a carbon-free fuel, offers the potential for zero CO2 emissions. However, hydrogen combustion presents unique challenges, including a much higher flame speed, wider flammability limits, and a propensity for flashback. Combustors designed for hydrogen or hydrogen-rich fuel blends require new injector designs, flame stabilization techniques, and materials capable of withstanding different thermal loads and potentially hydrogen embrittlement. Sustainable aviation fuels, or SAFs, derived from sources like biomass or waste oils, are also gaining traction. While often designed as drop-in replacements, their slightly different properties can necessitate adjustments to combustor design and operation for optimal performance and emissions.